Good afternoon. We're going to get started. Midterms tomorrow, of course, at 10. I'll plan on, I understand you guys have some of you may have a tutorial before that. I'd like to give you as much time as possible. So the rough plan is going to be we'll start right at 10 after. You'll be able to start, open your booklets and start writing in them. So maybe I'll make a few announcements beforehand. Just a little overview before 10:10. Any questions about anything for the course? Yeah.
Okay, for limit positions, is it always just when it's parallel and perpendicular? Is that what we're always looking for? It's just what's a good way to look at it? Because sometimes I don't know what's going on in the mechanism.
Yeah, this has been a common question, so I'll give a little general advice for finding limit positions. It's one of the trickier things in the course because there's not really there's not a formula you follow and you just learn it and do it. But you're right that I told you they appear when something is perpendicular or parallel. And the thing to look at is the input link. So wherever the input's coming, that's going to be perpendicular or parallel to the next link at some configurations. Those are good ones to check. So the way to find limit positions is basically do a little guess and check, sketch them out, and ask yourself, is that really at the limit? Or if I twist the input a little bit more right or left, or slide something, is that going to push it even further? So that's the first one to look at, is the input link perpendicular parallel to the next link, or however the motion's transferred to the next link. Yeah.
How do we do this in such a short time?
Yeah, in a short amount of time, some mechanisms with really weird geometry, like I gave you one on the homework with a slide that was at an angle with a slider going through it. That one's hard to just look at and know the answer. Like even if you've looked at a similar one before, that one's pretty tricky. So that one takes a little time. I think to solve that one, you have to sit down and sketch out a few tries. And that's how I solve them. I sketch out even 3 or 4. I make 3 or 4 little sketches, just rough sketches, and make some guesses. When link 2 is perpendicular to the next one, when it's vertical or horizontal, you can come up with maybe 2 or 3 candidates and then try and figure out which one is the limit all the way to the left or right. Yeah. Was there another question? Yeah?
My question is related to Emma's question. So tomorrow in the midterm, let's say we do get a limit position question, but we are not 100% sure maybe what it is or how to solve it. Should we just try sketching them out like you said? Will that get us partial marks?
Yeah, so I'm looking for how to give you partial marks. So the midterm is about you communicating that you know something about the mechanisms and techniques that I've taught you. So communicate to me what you're doing and what you're thinking. And maybe if you sketch out 2 and both of them are good guesses, and you say it's one of these, but I don't know which. You're most of the way there. So that's the kind of thing you can do. And if you just put a note on there of what you're thinking or what aspect of it you haven't figured out quite yet, and you can communicate that to me, that's a great way of empowering me to give you some more partial marks on it. Yeah. Any other questions? All right. So today we're going to, maybe the mic is not on. Let me try flipping this. How about that? Oh, yeah. There you go. OK, today we're going to finish up what I'll call the basic force analysis. Basic force analysis. So these are static force analysis problems, meaning we're going to assume that our mechanism's not in motion. So we're not going to have acceleration in our problem. And so we'll just look at forces in and forces out. And just a quick review from what we studied in the last 2 lectures. We're 2-force and 3-force links. And this is what we're always going to do with force analysis problems, is draw a free body diagram around each link. Each link independently. You have to study each link by itself. And if you can identify that there's no moments on a link, there's no twisting on it, and we're going to do a bunch of examples in the coming 2 weeks, and we'll ask this for basically every single link. Is there a moment? If not, are there only 2 or 3 forces applied to it? So this one, of course, has 3 forces and no moments. OK, and if that qualifies, you can take the shortcut. Right? These 2-force and 3-force links, we kind of already solved them generically. and we had these conclusions. For two force links, the forces are equal, opposite, and collinear. So two force links, you should, on an analysis problem, you should have an eye out for every two force link, and you'll get really good at finding them. Usually if their links are connected by turning pairs to other links, that's a good clue. Turning pairs can't transmit a torque through them. And if they only have two turning pair connections, already, you're done. You've solved that link. Equal, opposite, and collinear. You don't know whether the forces point in or out, so that might be a question mark that you'd have to solve by looking at the other links. And you don't know the magnitudes, of course. But otherwise, they just transfer motion straight through the link. So those are great, easy ones. Three-force links are a little more complex, but similarly, we just have a standard method of going through them. These three forces applied to our link all point towards a common location, and we called that K last time, this common intersection. These are the lines of action of those three forces, and they all point there. And so we solved a problem last time. We see how that point can solve for some unknowns, and then we do this thing called the force polygon to solve for the remaining unknowns. And a force polygon for three force links, they just have three forces. So it's just a triangle. I didn't label these, F3 and F1. So solving for the unknowns comes down to using this intersection point to find some directions, using your force polygon to find the unknown magnitudes. So these are three force links and two force links. So we're going to look for those where we can. Any links that are not, if a link is not a two force or three force, then we're just going to have to draw our free body diagram, and we're going to rely on our three equations, equilibrium equations. So we have sum of forces equals 0, and you can think about it like forces is a vector, so you could think about it like x components and y components as one example. Or you could do, these just have to be like two perpendicular directions. You could sum up forces in two perpendicular directions. So that's two equations, and sum of moments in the plane equals 0. So you have to write out some equations for those. Forces usually will be pretty straightforward. And then the moments are going to be we'll very commonly use moments to solve, because a lot of links that we have to resort to this more general method are when we have moments on links. Okay, so we're going to really frequently write the sum of moments equation for these other links. And sometimes we'll also use sum of forces as equations that we're writing out. So that's the basics. Today we're going to go through and look at basically the last remaining thing for the basic full solution is how do the forces move between the links. Had to be very gentle pulling it down. So we're going to look at kinematic pairs. That's connections between links. So that's going to be our main topic for today before we do the example at the end. Kinematic pairs. So we're going to look at force transmission between links. And remember, we have three or four types of kinematic pairs. And so we're just going to go through them. I'm going to start with rolling pairs. They turn out to be the easiest to look at. Rolling pairs. And we're just going to look at a really simple rolling pair, a wheel rolling on the ground. We'll call the wheel link 2 and the ground link 1 here. And so this is going to be a free body diagram. Okay, so we're going to draw forces on link 2. That's what I've chosen as my free body diagram. And it's very tempting to cheat a little bit when you're drawing free body diagrams. You're going to say, oh, I don't want to draw the link off by itself. Let me draw it as part of the mechanism and put forces on it. And you can get away with doing that. I'm going to do it here. But what you need to be clear about when you're drawing a free body diagram is, am I drawing the forces on link 2? Or am I drawing forces on link 1? So you just need to be clear about that. If you can be clear, then you can do that. Otherwise, or if there's a lot going on, you want to draw each link off separately. OK, so here, of course, If this is a pure rolling pair, there'd be no slip here. And to enforce the no slip condition, there has to be some friction here, right? So the friction, we're going to say it should act parallel to the slide here. So force of friction is going to be right along the sliding surface. And to keep the link 2 from going down into the ground, there's a normal force. Okay, and those are perpendicular to each other. So this is a way we can think about the interaction between those two links, and they're applied right at the contact. Right? And for rolling, there's only a single contact point. So that's why this is actually maybe the easiest kinematic pair to think about from force transmission, because you know right where the force is going to be applied. It's right at that contact point. Okay, as I said last time, when we're counting up forces, we want to know whether there's 2 forces or 3 forces or how many. Does this count as 1 or 2? They're applied at the same point, so if you want, you can add them and just count this as one input force. So you could do that if you wanted. So we could add these together, and we'd call that, or you could choose to call that, it's the force from 1 on 2. It's just those two added together. Force friction plus force of normal. Okay, if you wanted to, and of course that would be up and to the left here. You'd have to do some vector addition graphically, or you could calculate the components and figure out what those two are and add them up and apply it as a single force. Great, so this is rolling pair. What if there's slip? What if some slip was occurring? Right, if some slip's occurring, it's like we've maybe exceeded the friction, the static friction limit here, and some slip starts occurring. But in general, even if there's slip, you still might have friction there. You still might have friction. So in fact, for rolling pair, whether there's slip or not, this is the same diagram. Right? You can still have friction. Maybe if it's slipping with no friction, this would just go to 0. But this is the diagram's the same for rolling, or we'll say and, it's the same diagram, and roll plus slip. Same diagram, same forces. They're just applied at the contact point. And you need to know something about your mechanism to know if there's friction or not there. We'll assume that you know that, or you could neglect it, depending on what's going on. Any questions about our rolling pair? This one's pretty straightforward. Yeah.
Is it that the direction of friction, like it's not like something's gonna be in the same direction as motion, something's gonna be in the opposite direction of motion? Like, isn't it the direction of friction is like not known always, right?
Yeah, direction is not known. So everything that I'm drawing, even like these up here, these are directions that I define when I'm defining this vector. I call that thing F normal. And I just said it's up. It's pushing up on link 2, and friction force is pushing left. They could turn out to be negative. So if this thing is sliding to the right, the friction force will oppose it. So that's the friction force if it's sliding to the right. If it was sliding to the left, this would come out to be a negative number. And we're going to solve a problem at the end of today, and we'll look at negative forces or negative moments and how we can interpret those and communicate those clearly. So when you're doing a diagram, oftentimes you just have to guess. We know the direction. We just put it on there. That's a definition, and we can use it. And they can be positive or negative. OK, so this is rolling and rolling plus slipping. Our next one is a sliding pair. Sliding pair. And sliding pairs are kind of the weirdest. They're the trickiest of our kinematic pairs. So we're just going to do a slider on a straight slide to start. OK, so we have link 1 and 2. OK, so we might have friction, right? So friction you could add if you wanted. I'm just going to say for this case, let's just assume for now there's no friction. But just like a rolling pair, you could have friction here, of course. So that would be parallel to the slide. So I'll just say for this one, But in general, there could be friction. And then, of course, there's some force normal, just like our rolling pair. But the difference between rolling and sliding is that sliding pairs with a straight slide like this can have contact anywhere along here, right? Anywhere along here. So where is the force? We'll call it F12. That's our normal force. Where do you put it? It's tempting to say, oh, it should just be in the middle, right? And you'll say, oh, it should be balanced, right? It should be in the middle if it's going to be balanced. But depending on what else is going on with this link, it doesn't have to be in the middle. It can be anywhere along the contact point. And that's something you have to solve for. So that's an unknown. So I'm just going to put it here, and we'll put a note here. Can be anywhere along the contact surface, or contact edge, it would be here. Can be anywhere. And we're going to look at a slider, we're going to solve a slider crank problem at the end, and we'll look and we'll solve for where it needs to be. Okay, and you know, if this is a 2-force or a 3-force link, you'd say, oh, that's going to give me some clues. If other links are connected here, that can help me figure out where this force is. So that's going to be part of our solution. But that's our normal force. So it's perpendicular to, what is it? Perpendicular to the sliding surface. Perpendicular to the slide, or normal to it. Same as this one over here. So this is our sliding pair. That's our sliding pair. Let's do one that is curved. So what if I had this and it was pure sliding? If it was pure sliding going along here, then this is a simpler case. If you have a curved slide like that, instead of having a big contact edge, now you just have a contact point. And in fact, this looks just like our rolling, or it looks like our roll plus slip, but with no roll, right? So this one, a curved slide, turns out to be a little bit simpler. We just have that normal component. And it should be right at the contact point in this case. So curved slides, if there's a curved contact, just a single contact point. That makes it a little easier to study. And that would be the force from 1 onto 2. That's what I've drawn there. Yeah, do you have a question?
Yeah, so would this only apply to just one contact point? Because if there's multiple contact points, then there technically be normal force in different places.
Yeah, if there were 2 contact points, let me just draw a link with like, that, 2 contact points, then yeah, you said it could be anywhere between them. That's right.
Or if the link was the same curvature, then wouldn't you have the same problem as the snap pair?
Yeah, so that's a good one. We'll squeeze in a third one here. This is a link with the same curvature. So 2 curved links. This one looks like our straight. And this one's actually the hardest because the angle changes depending on where it is, right? So this one you need to think clearly. Yeah, it's going to be perpendicular to the slide, but you don't know the location. This one, perpendicular to the slide, but you don't know the location. It's kind of like it could be anywhere along there. So in reality, this one's a little bit unique because there's 2 contacts. So maybe the most accurate way of doing this one is you'd say there's actually 2. Right? They're both contacting. So what's really happening is there's a force here and a force here. Right? Force here and a force here. You could, what you could do basically is you could replace these by an equivalent single force. So that's a trick that we'll look at later. You could replace these 2 by a single force. And in fact, we kind of pulled that trick here already, a little bit hidden behind the scenes here. I said there's like 1 force, but in reality, you can have a contact, and the load could be spread over this. And that's what's going to happen with real links, a real slide. It's going to spread the load over. depending on how stiff it is and whatnot. And it might be multiple, which you could approximate as a single equivalent force. And we'll talk about what equivalent force is later. Basically, it should balance the moment out from it. Yeah, that's a good qualifying question. So these are some variations on our slide. Any questions about those? Great. And our last one is the turning pair. Turning pair. And turning pair, in a way, is a simple one. So let's say we have links 2 and 3 connected by a turning pair. You'd say, how can they transmit a force between them? And what we're going to do here is we're going to kind of zoom in on the bearing. Let's zoom in on what's going on there. So I'm going to draw those links a little bit bigger here. And I'll draw them kind of as a more of a cross-section kind of drawing here. So there they are. And now we can see like there's the 2 links, and between them there's this pin. And every turning pair may have something going on there, like maybe there's actually a ball bearing with a bunch of balls going around. So for now, let's just assume it's a pin. So it's like a little piece of, a little cylinder of metal that's stuck through the 2 links. And I'm going to just assume for now, let's just assume that this is attached to link 3. So it's like it's part of link 3. Think about it like you 3D printed this link and it has a little pin sticking out and it goes through link 2. And so we can pivot about that point. And we're going to try and figure out how can that pin transmit forces. And of course, the interface between them is along the edge of that pin. Right? It's along the edge of the pin. So what's really going on there, right? There's sliding contact, right? It's a sliding contact and it's curved. So it looks kind of like that top one. It's a curved version of a slide, but it's curved all the way around. So the actual force transmission, the interface between them is along a curve. Okay, and curved interface means, which is sliding, means the force can be transmitted any direction, right? It has to be normal to the slide, but the slide is all the way around. So our conclusion here is that the force transmitted, we'd be talking about for example, F23, the force from 2 onto link 3, can be in any direction. Can be in any direction. Okay, and that makes sense. If you have a pin joint, think if you were holding link 2 and I was holding link 3, we could kind of fight against each other, and I could pull up like I'm fishing. I could push down. I could push up and down any direction, right? It can transmit force any direction. So that's our conclusion for F23, the force between 2 links connected by a turning pair. And of course, there's no moment. No moment, unless you assume there's some friction. Let's just say that there was a sticky bearing. Then maybe there is some friction would appear as a moment being transferred. So we'll say no moment if friction equals 0. Okay, and that's going to be a really common assumption we make. Because a lot of actual mechanisms, a lot of actual machines, this friction in the joints is pretty small compared to the other forces involved. And if it's not small enough, you could make it smaller by replacing this pin with a ball bearing or some other high performance bearing that makes the friction nice and small, and you can usually assume the moment is 0. Not every case though. Okay, any questions about our turning pair? Turning pair is pretty straightforward, pretty straightforward one. So the last thing we're going to do today is we're going to look at a slider crank mechanism. Let me get my board straight here. I'm just going to do it here. This is going to be our example. And a slider crank has basically all the elements that we've talked about. It doesn't have all of the funky slides, but it has a slide in it, turning pairs, and transmission between the links. So try and draw roughly similar to my geometry here. Let's make that a little bit longer. Okay, so this is our slider crank. Ground, link 2, 3, and 4. And for this problem, let's assume that there's some load here. We'll call it P. It's acting horizontally. And let's say we know something about that. Maybe it's caused by an explosion in an internal combustion engine piston, or something else, 1,000 newtons. We know what it is. Okay, that's our input. And let's say this needs to be balanced. Let's say that needs to be balanced. And the other side of the mechanism, we have some connection to the outside world. It could be like an electric motor or something on link 2. So let's say there's a motor here. At this base pivot point O2. And I chose to draw my moment counterclockwise. That's going to be the standard that's nice to use, as counterclockwise is positive moments. But we're going to see what happens with this moment later on. So we'll see if that's the correct direction to balance it. You can probably look at this mechanism. It's not that complex. You can probably guess whether that's correct or not. Is that the moment that the motor needs to apply here? If it's not correct, we'll see what to do, whether we change this to the other direction, the arrow, or whether we can just put a negative number on it, and we'll think about the implications of that. Okay, for this example, let's neglect some aspects. Let's neglect a couple forces. We talked about a whole bunch of possible forces, so let's assume that there's no acceleration. So mass times acceleration, we're going to say that's really small. The links have no weight. Let's just assume that they have no weight. Maybe they're very lightweight compared to, right, this is a big load, 1,000 newtons. Maybe they weigh 1 newton each, and we'll just choose to ignore that. Or maybe this is operating in the horizontal plane. Then the weight wouldn't affect the motion. We're also going to ignore friction. Things like fluid drag. Let's ignore all those things. So this makes our problem as simple as we can. We have one input and one output. And really the question we're going to ask, question doesn't have to do with what is the input and what's the output. It's going to be what moment, that's the unknown, is required to balance P. Okay, to balance P. And this means that our mechanism, we need to, another way of stating this is what moment will put this mechanism into equilibrium. Okay, and this makes a lot of sense for static problems. It's just the moment required to keep the mechanism from moving. Later, after reading week, we'll study problems that are actually moving, and we'll still use this balance or this equilibrium concept. We'll kind of extend it to those problems. But for now, let's just assume it's not moving. Okay, so our task now, we have to go through each link. And let's see what we know. We're going to draw a free body diagram of each link. And we're going to be on the hunt for 2-force or 3-force links where we can. So I'm just going to start where the input is, the thing that we know. Unlike velocity or acceleration polygon problems, where you step through the solution and you start at the input and you go through and you solve it all the way to the output, in force problems, usually we have to do a free body diagram of all the links, and then we can start solving it. So we'll see how that plays out here. So here's link 4. We're going to put what we know. P is 1,000 newtons. That's known. What else do we have? 4 is sliding on the ground. It's sliding on 1. So sliding kinematic pair, it's up at the top board there. That's going to be here. And where do we put that? I drew it in the center, but it could just as, just as valid, it could be over here. We don't know. It's just vertical. So for now, I'm just going to write the direction on there. It's up or down, but we don't know where it is. So we'll have to have more information to solve for that. What else do we know? Link 4 is connected to link 3. And they're connected by a turning pair. And a turning pair only exerts forces, right? So that would be the force from 3 on 4. Or F3-4. Force from 3 onto link 4. And where is that applied? It's right at that point. So we'll call that point D. But what's the direction? Until we look at link 3 in more detail, we don't know the direction. So we'll just say, that's just my, my notation there. Force 3-4 is applied at D. But we don't know its direction yet until we think about link 3. Okay, so what do we have here on link 4? We have 3 forces. I'll take your question in a second. We have 3 forces and no moments. So we should say, this is great. This counts as a 3-force link. So you're going to be the detectives as you solve these problems, and you're putting together all these clues. 3-force link, we can go into 3-force link mode and say, okay, all these forces need to intersect at a common point, right? Common intersection point for 3-force links. This is good. So 3-4 is at D. D is right there, right? P is right through the center, also pointing at D. So right off the bat, we know F normal should also point at D. So for this one, we can say, now that we've realized it's a 3-force link, we can already start putting the locations of some of our forces on there. It should point right at that common intersection point K. Was there a question, or maybe I answered it? Yeah.
No, I mean, now that we know, that kind of answers the question, but from before, like if we just looked at the mechanism, could we already assume that the force, or F3-4, would act in the direction of 3, or can it
So you're jumping to link 3, which is nice. I like that you're doing that, and you're saying link 3 should transmit right along its length, and that's correct. Yeah, that's correct. We'll draw it out here. It's a 2-force link, right? That's how you know that. That's how you know that. Okay, so this is all we can do for this at this point, right? We don't know enough to start the force polygon here. We don't know quite enough to solve that one. So let's move on to link 2. Oh, sorry, link 3, the next one. And many of you probably already looked at it and said, okay, link 3 is the easy one. Link 3 just has forces at B and D, and they're turning pairs, so there's no moments. No moments applied. So there's going to be forces here equal, opposite, and collinear. And let's get these, let's label these here. This is the force from 4 onto 3. And I just chose them to be pointing in a bit arbitrarily here. We'll see if it's correct once we solve the problem. Over here we have force from 2 onto 3. Force from 2 onto 3. So we know these are the same magnitude. Same magnitude, but opposite direction. So link 3, it just transmits right through. So yeah, you were right. So now we can kind of back propagate our knowledge. And that's going to be what force problems are always going to be about. You start with one, figure out what you can. Once you get stuck, move on to the next link, and you'll back propagate information. So all of a sudden, we know the direction of F4-3. And F4-3 is the opposite of F3-4. Okay, and it's along length 3. And I should draw it in the opposite direction. Opposite direction, so down and to the right. Okay, along length 3. Any questions about that one? That's a key step for our problem. Great, but we still don't know how to calculate, we haven't calculated the magnitude. So let's go back to our link 4 and say, do we have enough information now to do it? We have directions of all of them, and we have the magnitude of 1. And if you think back to last lecture, that's 3 force links. That's enough information to solve our force polygon. So as soon as we have directions, a few directions, and a magnitude, we have enough to solve it. So first we put on what we know. P is the only one that we know. Okay, and you need to do a scale diagram here. So you choose a scale that makes sense for you, that fits on your page. Maybe do 1,000 newtons is 5 centimeters on your page, whatever fits in nicely. Define your scale, and then put the other directions on. So I'm going to put 3/4 over here. Okay, and the normal force is vertical. So that happens to be, for this one, happens to be a right angle here. Great, and this is enough. We've solved the polygon here. And you'll recall from last time, these need to add. Our polygon is an addition. P plus F3/4 plus the normal force equals to 0. Plus, plus, plus. That's what we always have for force polygons. So it needs to go around the loop. P started off to the left, so that's like a counterclockwise loop here. So we can put the arrowheads on these other two, and we can get the directions. Okay, so at this point, now we're able to check if I put some of those on correctly. So let's check if I drew it. Normal force should be up. I drew it right. Okay, otherwise maybe we would choose to correct that one. F3/4 is down to the right. Along length 3, I drew that one right as well. And as you solve a few problems, you'll get better at guessing those, so you don't have to correct them. You know, it needs to balance. P was pointing to the left. Something needs to point to the right to balance it. So you'll get better at identifying those right off the bat. That's our force polygon. We can measure on it. I'll just eyeball this one here. Let's say F3/4 is, what do I have, like 1,200 newtons, and the normal force is 1,100 newtons. Okay, you measure it on your ruler by doing a detailed diagram for accuracy. Good. F3/4, 1,200 newtons. Now it propagates. Now we've propagated information forward. F3/4 is the opposite of F4/3, but same magnitude. So propagate it, same as F2/3. Okay, so now we've propagated all the way to point B. So now we know the force at B is 1,200 newtons. It's from link 2 onto link 3, and it's along link 3. So this problem, it turned out, we didn't even have to look at link 2 yet, and we were already able to solve 3 and 4 completely. Okay, other mechanisms, you may have to go through more links before you can propagate information back. So now we're on to our last link. Link 2. So let's do a free body diagram. So here's link 2. It's connected to link 3 at B. So it's going to have this equal opposite force 3/2. Okay, we already know the magnitude, 1,200 newtons. Great. It's along link 3, so graphically you'd lay this out on your page. You know, to do this accurately, you need to have multiple angles correct. You need to have the angle of link 2 correct and the angle of this force. So for this one, maybe you would, for doing inaccurate measurements, as we'll do in a second, you would keep it on this diagram, or you could copy link 2 here, but you have to be accurate if you do that. Okay, what else do we have? Are there other forces on this link? Or is this it? Sorry? Moment 2, yeah, moment's on there. Moment's on there. Okay, is that everything? This is a free body diagram of link 2. I see you pointing up, yeah. The ground. The ground. Is that what you said? Yes. Yeah, the ground. So this ground point is a turning pair as well, and that might also have a force, right? So anytime a link's connected to another something, there's likely a force there. It could happen to be 0. I mean, we can look at this link and say, to be balanced, something needs to oppose this force, right? And a moment can't oppose a force by itself, right? So if we did sum of forces here, those should equal 0. These are the only forces on our link now. The only forces are F32 and F12. So they should be equal and opposite, right? So this is great. So all of a sudden, equal and opposite. Same magnitude. Great, that's F12. And right, sum of forces equation, we don't worry about moment in our sum of forces equation. It's just the applied forces. Now we'll ask ourselves, does it count as a 2-force link? There are 2 forces, but there's also an applied moment. So this is not a 2-force link. I'll put it in quotes, because of course there are 2 forces, but it's not going to count as our special case. Because our special case, we used the fact that there were no moments to derive that equal opposite collinear thing. And of course, the forces are not collinear. They are equal and opposite, but they're not collinear. It's not a 2-force link. So in this case, we have to rely on sum of forces and sum of moments equal to 0. That's all we can do here. So we already did sum of forces, and that gave us the direction and magnitude of F12. So the remaining thing to do would be sum of moments equals 0. Okay, and as I said before, sum of moments, you can choose which point to sum your moments about. So you could do some examples. Sum of moments about B equals 0. That's a fine one. Sum of moments about B. So F32 goes through B, so it wouldn't appear. But you'd have your moment, and you'd have F12. Or another logical one you could try is sum of moments about the base point, O2. And that's the one that makes the most logical sense to me. Because F32, that's the one transmitting force in here. So let's do this one. You could do either one. Either one would work. So let's do this. Sum of moments about O2. We have our moment applied, an applied moment. In applied moments, it doesn't matter where they're applied. You may think about it, the motor is twisting here, but once a moment is applied to a rigid link, its location doesn't matter. It's just a moment that's applied. So no matter where M2 is actually exerted by a motor or whatnot, we just put it into our equation as M2 here. Okay, and I'm going to say counterclockwise is positive. You just need to define your own standard here. That's the one I like to use. Counterclockwise positive for moments. It's not a global fundamental standard. It's just the one I'm using for writing this equation. Okay, M2 is counterclockwise, so positive. Okay, we're doing sum of moments about this point. F12 goes through that point, so it doesn't exert at any moment. So we're just going to have F32 times some moment arm. And we did this last time. The moment arm needs to be the distance between our force and the point about which we're summing. So you can't do distance this way. It has to be perpendicular distance. That distance there, that's our moment arm. Okay, so you lay this out accurately on your page, and you measure D. And you can plug that in here. This is our sum of moments, and we sum to 0. So what we're solving for is M2. We're solving for M2. Before we solve for it, did I get the direction right? Positive is counterclockwise. So is F32 causing a counterclockwise or clockwise moment about the base point? It's pointing this way, about this point, so counterclockwise. So plus is good. Okay, so now we can solve for M2. Negative F32 times D. So we just plug in our numbers. F32 we propagated from the other links, 1200 newtons. And D, we'd measure. I didn't give any lengths on this thing here. Let me just use an easy one, 10 centimeters. So our moment, we'd calculate negative 12,000 Newton centimeters. You can convert that to Newton meters, that'd be 12 then, 120 Newton meters. So this is a tricky one. We get a negative moment as a result. So we've completed the problem, but the last thing we have to do is interpret this answer. And how do you communicate this, right? I drew it this way, but we got a negative answer. So that's like I got the direction wrong. And if you think about this, think about you pushing there. To counter you, I would need to twist link 2 clockwise to counter you, to balance you, pushing that way. So this was incorrect. So you have 2 choices for communicating moments, which turn out to be negative. One is to say it's negative and leave your direction here. But I think that's a little bit confusing, a negative moment. So a better way would be change it to positive and just say what the direction is. So that's my suggestion to you for non-ambiguous moments. Non-ambiguous, to be really clear, report your moment as a positive number. So we got 120 Newton meters, and it's clockwise, right? There's no way to misinterpret that. It's positive, it's clockwise. It's the same thing as a negative counterclockwise. But this one is not ambiguous. This one, I think some people may interpret that and not be, it's not as clear. Any questions about our process? This is our propagation process. We went through a bunch of kinematic pairs. Next time we're going to study links that have a whole bunch of forces on them and see what to do before we get to dynamic problems coming up after that. So thanks everyone. We'll see you tomorrow morning.